We learn some properties of liquids and vapors in chapters 5 and 6 of Felder and Rousseau. Let's see if we can use some of that information to determine the contents of a propane cylinder. This is the type that you would find in any backyard barbecue grill. It's a cylinder, a pressurized tank, that contains liquid propane with vapor in the headspace. Typically, these are charged with 20 pounds of propane, and the volume is 5 gallons, approximately. Can we use the information about liquids and vapors to determine how much liquid and how much vapor is present? First, let's convert these units to something else. The gallons, let's convert that to liters. And so we have 0.264 gallons per liter. And so this equals 18.9 liters. 20-pound mass, let's convert this to grams. So we have 454 grams per pound mass. And that equals 9,080 grams. Now we know the volume of the gas. It's actually a vapor, but we'll call it a gas here. The volume of the gas is equal to the mass of the gas divided by the density of the gas. And likewise, the volume of the liquid is equal to the mass of the liquid divided by the density of the liquid. We also know that the volumes must add up to 18.9 liters, and so we can say that Vg plus VL equals 18.9 liters. And the masses must add up to 9,080 grams, and so we have Mg plus Ml is equal to 9,080 grams. This is 4 equations with 4 unknowns because we can calculate the densities of the liquid and gas. So by solving these 4 equations and 4 unknowns, we'll find out how much mass of gas and liquid there is, and likewise how much volume is occupied by these 2 phases. The first thing we'll need to do is calculate these densities. We can just look up the density of liquid propane. In Wikipedia, it's given as 493 grams per liter at 25 degrees C. It's a weak function of temperature, but we'll assume our system is at 25 degrees C. That's room temperature about. For the vapor, we can use the ideal gas law if we assume it's an ideal gas. And if I write the ideal gas law, PV is equal to nRT. That's the pressure times the volume is equal to the number of moles times the gas constant times temperature. I can rearrange this to a molar density, which is N over V, number of moles per volume, is equal to P over RT. And if I multiply through by the molecular weight, grams per moles per liter turns into grams per liter, which is the density. So I'll write that the density of the vapor is equal to the pressure times the molecular weight divided by RT. So I can calculate then the density of the vapor, but I don't know what is the pressure. The propane tank's under pressure, and it is the vapor pressure of propane at that temperature. How can we find that? So Antoine's equation can be used to calculate the vapor pressure. That's Antoine's equation. It's usually of the form, the log, and this would be usually base 10 of the vapor pressure is equal to a constant plus another constant over the temperature plus yet another constant, C. And in Felder and Rousseau, there is a table of Antoine's constants for a variety of chemicals, unfortunately not propane. So we'll have to go elsewhere for these constants. One thing to point out, though, is that be careful that different tables of Antoine's constants utilize different units. For instance, Felder and Rousseau's table has pressure in millimeters of mercury and temperature in degrees C. But in the NIST, National Institute of Standards and Technology, their table has units for pressure of bar, which is almost an atmosphere, and temperature is in units of Kelvin. So, looking that up then, A is equal to 4.53678. We probably don't need to use all of those significant figures, but they're available. B is 1149.36, and C is equal to 24.906. So, usually what you'll do is put the equation in this form. The vapor pressure is equal to 10 to the A minus B over T plus C, like that. And calculate T plus C first, then invert it and multiply by B, then take the opposite of that and add it to A, and finally take that quantity and raise 10 to that power. Now, with these constants and 298 degrees Kelvin, we get that the pressure is 9.49 bar, which is equal to about 9.37 atmospheres. Okay, now we can calculate the density of the vapor. The density of the vapor is equal to pressure, which is 9.37 atmospheres, times the molecular weight, 44.1 grams per mole, divided by R, 0.0821 liter atmospheres per mole degree Kelvin, and then divided by the temperature, which is about 298 Kelvin. Let's check the units to make sure that they work out correctly. Kelvin cancels. Atmospheres cancel. moles cancel, and I'm left with grams per liter, which is what I wanted. So this is equal to then 16.9 grams per liter. Now, I know the density of the liquid and density of the vapor, and I can plug those into those four equations with four unknowns. Again, the volume of the gas is equal to the mass of the gas divided by 16.9. That's grams divided by grams per liter. The volume of the liquid is equal to mass of the liquid divided by its density, which is 493. Now we combine this with the volumes adding up to 18.9 liters, and the masses adding up to 9,080 grams. So it's grams and that's liters. The solution turns out to be that the volume of the liquid is equal to 18.4 liters. The volume of the gas is equal to 0.5 liters. The mass of the liquid is 9,072 grams, and the mass of the vapor or gas is equal to 8 grams. So you can see from this example that the vast majority of a propane tank is in the form of a liquid with just a little bit of a vapor space at the top when it's fully charged. We can ask if this gas really can be treated as an ideal gas. We can use any one of a number of equations of state. These all require the reduced temperature pressure, which is calculated from the critical temperature and pressure. So the critical temperature and pressure from Felder and Rousseau are 369.9 Kelvin and 42.0 atmospheres. And also the eccentric factor is 0.152, used in some of the equations. The reduced temperature is the actual temperature, 298 Kelvin, divided by 369.9, which is equal to 0.806. And the reduced pressure is equal to 9.36 atmospheres divided by 42.0 atmospheres, or 0.223. The virial equation gives a Z factor of 0.844. The SRK equation gives a value of 0.829, and the compressibility factor equation of state, those are the charts, gives a value of 0.85 approximately. So those are all in agreement, more or less. Let's use the compressibility factor equation of state. Now it's in kind of a sketchy region of the compressibility factor chart. This is a saturated vapor, and I'll leave that to a more expert in thermodynamics as to whether this is really a good value or not. But the density of the vapor then would be, instead of 16.9, we'll divide by 0.85. It's 19.9 grams per liter, and that adds a couple grams to the vapor. But it's not a big difference.